This is triangles part 3. This time, instead of trisecting, I'm going to cut the sides of the triangle into 4. My conjecture is that that will give us 4 squared congruent triangles, or 16. And if we leave it as one row of similar triangles along one side, there should be 7 similar triangles there, plus one larger one makes 8, and we can then cut any of those and produce an extra 3 each time we cut. Let's just do it and make sure that that's correct. Draw a circle, center B, radius A on 4. Draw another circle, center B, radius B on 4. We have 2 circles. Find some intersections of the smaller circle with line segment A, the larger circle with B. Hide the circles. Draw a line segment DE, and because BE is a quarter of BC and BD is a quarter of BA, triangles BED and BCA are similar, and therefore DE is parallel to AC, and so on. Let's do a little zigzag construction. Instead of doing circles, I'm going to do it the quick way and use a parallel line. So this is parallel through D, parallel to BC, and then through E, parallel to AB, through that intersection, parallel to AC, through that intersection, parallel to AB, through that intersection, parallel to AC. Line segments, let's make sure that these are segments. Then I can erase the parallel lines. And another one there. Hide the parallel lines. And I have, as I predicted, which is nice, 1, 2, 3, 4, 5, 6, 7 small triangles plus one larger one makes 8 similar triangles. Of course, if I continued my construction, I'd have 7 and then 5 and then 3 and then 1, which would be 16 small congruent triangles, which just occurred to me. I don't know which of Quirko's habits of mind this is. I guess it's multiple points of view, looking at something a different way. Here's a lovely little proof that the sum of consecutive odd numbers starting from 1 is a perfect square. We'd have one triangle at the top, then a row of 3, then a row of 5, then a row of 7, and we'd get 16. That's just a little aside that I just noticed as I was doing it, which is kind of cute. So 7, 8 similar triangles. If we then wanted to use our little midpoint construction, make sure we get the right one, of that line segment, that line segment, that line segment, draw the segments, instead of having 8 similar triangles, we'd have 11 similar triangles, and then 14, and then 17, and so on. So in our triangle constructions part 1, we managed to get 7 similar triangles, then 10, then 13. In part 2 I got 6, then 9, then 12. In part 3 I got 8, then 11, then 14, and it looks to me as if we've covered every possibility from 6 onwards. So here's a little Word document I prepared earlier. This is for the 4 section, 16 congruent triangles, 7 along the bottom, plus 1 is 8. Cut the larger triangle or any of the smaller ones into 4, as I just did here. Then we get an extra 3, which is 11. Cut it again, we get 14, or in general we get 3n plus 5 similar triangles. And I've generalized that to say that if we have a K section, so you can cut it into, you can bisect where K is 2, or trisect with K is 3, or K is 4 as in this case, but we could equally well do K is 5, 6, 7 and so on. We'll get K squared congruent triangles. So we can get all the perfect squares. We can also get, generalizing the similar triangles, this row along the bottom, which is 2k minus 1, plus the one at the top gives us 2k, and then any cut of any of the smaller triangles increases the number of triangles, similar triangles, by 3. So that gives us 2k plus 3n similar triangles. K has to be at least 2, n has to be at least 0, because we can cut none of those smaller triangles. If we let k is 2, then that gives us 4, 7, 10, etc. Except if we've got 4 triangles, I guess that congruent. That was part 1. K is 3, that was part 2, the trisection, that gives us 6, 9, 12. K is 4, gives us 8, 11, 14. We've covered everything greater than 5. So far we can conclude, it's my generalization, that I can get k squared congruent triangles and any number of similar triangles greater than 5. And of course, here's where my Cuoco habits of mind comes in, because I actually want to know whether I can do better than that. So I guess this is, I'd call it curiosity. I don't know quite what he calls it, but I think curiosity is critically important. What I think I'm reasonably sure of is that by drawing lines parallel to the original triangle, as we've done in all of these, by bisecting, trisecting sides, etc., I think that's actually all we can do. I don't think we can do any other number of congruent triangles or any number of similar triangles that's 5 or fewer. So I'm going to need to do something a little bit different, and that's part 4.